everyone! So this is the Chem001C video for this week 4. I'm Haley and we're just going to go over the first worksheet. So for the first question, it says in a Bronsted-Lowry, what's the definition of acid and bases? What is an acid? So an acid is So in order to solve this question, I think we should first think of how we would put an acid in an equation. For the Bronsted-Lowry definition. So usually an acid is represented as HA. So we can have HA, which is aqueous. And we can add water. So that's H2O, which is a liquid. And then that dissociates into H3O+, which is your hydronium ion. And that's aqueous. Plus A-, which is from your original acid. That's aqueous as well. So from this equation, we can think about what happens to HA as it travels across this equation. So HA dissociates into A-, and it also adds a character to this H3O. This H3O is actually from the water that we had before, but as you can see, there's an extra hydrogen added. So that means that this acid is giving a hydrogen to water. And because it's giving this hydrogen, it can be seen as a hydrogen donor or a proton donor. So the answer to this question would be proton donor. So for number 2, a solution with a pH of 9.5 has a pOH of blank. So we're searching for a pOH when we have the pH. There are many different ways to do this. You can either use Kw or you can use the pH plus pOH equation, because pH plus pOH should equal 14. This one is probably simpler to use than your Kw, because your Kw is equal to 1 times 10 to the negative 14th, or it's equal to the concentration of H plus, or H3O plus, and the concentration of OH minus that should be present in your solution. So from using the bottom equation, I can just plug in our pH that we have. So that's 950 plus pOH plus 14, or equal to 14. And then we can just rearrange this equation to find pOH. So pOH would equal 14 minus 9.5, which would equal 4.5. So 4.5 would be our answer to this question. So for the third question, what is the concentration of hydroxide ions when H plus is equal to 1 times 10 to the negative 7 in water at 25 degrees Celsius? So for this one, we can actually use our Kw equation, because we have the H plus concentration. So Kw, again, is equal to the H plus concentration multiplied by the O minus concentration. And that equation is all equal to 1 times 10 to the negative 14th. So we can just plug in our H plus. So that's 1 times 10 to the negative 7th times the concentration of OH is equal to 1 times 10 to the negative 14th. So even without a calculator, you can see that the OH concentration is going to be equal to 1 times 10 to the negative 7. And this is in molar. Remember, this is significant because if both H plus concentration and OH minus concentration is equal in a solution, that means that the solution's pH is neutral. So for number 4, what is the hydronium ion concentration in a solution of acetic acid? The Ka for acetic acid is 1.8 times 10 to the negative 5th. Remember that the hydronium concentration, so that's H3O plus, is equal to, or is basically the same thing as the concentration of H plus in a solution, and these are interchangeable, at least for this equation. So first, I think it would be easiest to find the equation, or the chemical equation for this solution. So acetic acid would be CH3COOH. This is the formula for acetic acid. And then since acetic acid is a weak acid, we can have equilibrium arrows. And then it dissociates into CH3COO minus plus H plus. So from here, you could do an ICE table in order to figure out your concentrations at equilibrium. So ICE, you know that your initial concentration for the acetic acid is what is given to you, so that's 0.01 molar. And then because that's the only species that's inside your solution at the moment, the other 2 species on the product side would be 0. And then you can calculate the change, and the change is always going to be adding to the reactant, to the side of the equation that doesn't have any concentration. So we're adding X on this side, and we're subtracting X from the concentration that's already there. So for your equilibrium, put 0.01 minus X, and then X and X. We can form our Ka equation by putting products over reactants, so that's concentration of CH3, COO minus, and H plus over the concentration of our acetic acid. And if we were to plug in our equilibrium values from the ICE table, that would be X squared over 0.010 minus X. And then this will be equal to our equilibrium constant, which is 1.8 times 10 to the negative 6. So from here we can find X. Either we can use the quadratic formula, or because our Ka is extremely small, we can disregard the X on the bottom and use the 5% rule. So this X on the bottom can be disregarded because our Ka is small. So if I disregard the X, then our X will be equal to 4.24 times 10 to the negative 4. And remember that X is also equal to our concentration of H plus. Again, to make sure that this X is valid, we have to use the 5% rule. So I will show my work for that. The 5% rule would just be our X that we found. So 4.24 times 10 to the negative 4, all over the initial concentration that we have. And that would be 0.010. And this would be multiplied by 100 to find out that it's 4.2%. 4.2% 4.2% is less than 5%, so it is okay to disregard this X on the bottom. If I didn't want to do this because 4.2, although not a significant amount, is still worth figuring out whether we can use the quadratic formula. So using the quadratic formula, we come up with an equation that looks something like this. So this would be, of course, without disregarding the X that we did at the bottom. And then we'd get an X that's equal to 4.15 times 10 to the negative 4th, which is not significantly different from the X that we had before. So either concentration would be correct for this problem. So this one, or the one we found here. So for number 5, a solution of a monoprotic weak acid has a pH of 3, and what is the pKa of this acid? So because they don't tell you what the identity of this acid is, we can just use the normal equation that I used before in number 3, I believe. So HA. And we're going to have equilibrium arrows this time because it says it's a weak acid. So that's HA dissociates into A minus plus H plus. And from here we can do the same thing that we did in problem 4 and create our ice table. So HA has the initial concentration of 0.1. Then everything else is at 0 because they haven't formed yet. So then our change is going to be minus the initial concentration that we had and adding it to the product side. So equilibrium concentrations will be 0.1 minus X and 2 X's. So from here, we know that the pH is 3.0, even if we don't know what the Ka is. So because we know what the pH is, we can find out what the concentration of H plus will be at equilibrium. We can find this using the pH equation. Remember that pH is equal to negative log of the H plus concentration. So we can rearrange this equation to solve for H plus concentration, and that would be 10 raised to the negative pH, so that would be 10 to the third. So if H plus concentration is 10 to the third at equilibrium, we can assume that X is also equal to 10 to the third. So now we can form our Ka equation, and our Ka equation would be equal to our X squared over 0.1 minus X. And because we know that X is 10 to the negative third, we can put 10 to the negative third for X. And 0.1 minus 10 to the negative third. And then we can solve for our Ka. So from this, we find that our Ka is 1 times 10 to the negative fifth. And from there, we can find our pKa using the same pH equation. So pKa is going to be equal to the negative log of the Ka. So that would equal to the negative log of our 1 times 10 to the negative fifth, which is equal to 5.0. So 5.0 is our pKa of this acid. So for the last question, it asks what's the pH of a solution of ammonia. The Kb value for ammonia is 1.8 times 10 to the negative fifth. So I think the first thing we should do is find our equation for this reaction. So I'm going to start with H2O, that's a liquid, plus NH3. NH3 is ammonia, of course. And we're going to have equilibrium arrows because it's a weak base. And this weak base dissociates into NH4 plus OH minus. And now we can use our ice technique. So H2O is a liquid, so it's not included in this table. NH3 is 0.20 molar. And then the other two have not formed yet, so it's 0. The change will be minus x and plus x for the product side, much like the last problem. And it'll be 0.2 minus x, and x for equilibrium concentration. So then our Kb is going to be products over reactants per usual. So concentration of NH4 plus, concentration of OH minus, over concentration of NH3, and that's going to be equal to our equilibrium value, so that's x squared, over 0.2 minus x, which is going to be equal to our K equilibrium. That's 1.8 times 10 to the negative fifth. In this equation, because our K equilibrium value is significantly small, we can disregard the x on the bottom. And we can use the 5% rule to solve for this. If we disregard the x on the bottom, our x is going to be equal to 0.0019, which of course is equal to our OH minus concentration. Again, I can show that this is appropriate by finding the 5% rule. So that would be this concentration of x, so 0.0190 over 0.20, our initial concentration, multiplied by 100, which gives us a value of 0.95%, which is smaller than 5, so we're able to use this rule. If you want to use the quadratic formula, we'll end up with an equation that looks like this. This is without disregarding the x. So then for this equation, our x is equal to 0.00191, which is not significantly different from the time at which we disregarded x. So now that we have the OH concentration, in order to find pH, we can either find POH first, or we can use the Kw equation to solve for H plus concentration. In this case, I'm going to use POH. So our POH is equal to our negative log of the OH concentration. So that's going to be 0.00190 in this case, and that's going to end up being 2.7. So in order to find the pH, we can use POH plus pH equals 14. So that means that our pH is going to equal 14 minus 2.7. And that's going to be 11.3. And that's our pH for this equation. It makes sense because ammonia is a base, so our pH should be basic. Alright, and that's it for this worksheet. Thanks for watching.